Okay, kita sambung semula. Okay, yang ni adalah 7.2. 8 sebenarnya ni, chapter 8 bukan 7. Magnetic force on electric current. So during the 18th century, many scientists sought to find the connection between electricity and magnetism. Do we have any connection between them? Yes, we have a connection. But in terms of what? How the correlation should be? So a stationary electric charge and a magnet were shown to have no influence on each other. Stationary electric charge and magnet seems like they have no influence on each other. But in 1820, Hans Christian Ørsted found that when a compass is placed near a wire connected to a battery, which the wire actually carries the electrical current, so the compass needle will be deflected. This is an indication that the electric current would produce magnetic field. Remember, stationary electrical charge doesn't have any influence on the magnet bar, but a moving electrical charge, meaning that the electrical current, a wire which carries electrical current, moving charge, it will have some effect to the magnetic field. How the effect looks like? So, like this, it's like this. A compass needle placed near a straight section of current carrying wire like this. If we have a current carrying wire like this, so if you place the magnet, the compass nearby the wire, it will show some deflection on the direction of the compass. So the compass needle placed near a straight section of current carrying wire experienced a force, causing the needle to align tangent to the circle imaginary around the wire. So it shows circle like this. So if the circle is like this, where is the direction of the electrical current? We actually can determine that using our right hand rule. See, we use our first right hand rule over here. The magnetic field lines produced by a current in a straight wire are in the form of a circle with the wire at their center, like this. If the current is moving that way, they will generate magnetic field. And this magnetic field will deflect the direction of a compass. The direction of a compass will align with the magnetic field generated by the current carrying wire. So how do we know the direction of the magnetic field of a current carrying wire? Using our right hand rule. So the thumb is showing the direction of the current, the movement of the charges. And the rest of the fingers is showing the direction of the magnetic field line. See the direction of our finger? It curves like this. It is counterclockwise. So therefore, the direction of our magnetic field line generated by the current carrying wire is following the direction of counterclockwise. This is our first right hand rule. We have two right hand rules and one left hand rule. So we have three rules to be memorized. So the direction of the magnetic field line is indicated by the north pole of the compasses using our right hand rule. So if we have a strangely looking current carrying wire like this, looks like a loop, okay, and the current is moving like this, okay, so how do we know the magnetic field line of this peculiar current carrying wire? Still using our right hand rule, we follow the direction of the electric current. So our thumb is following the direction of electric current, and the rest of the fingers, they are showing the magnetic field line. So it goes like this. Funny. Dia akan masuk sini, keluar sana. Dia akan pusing. It is in a closed loop. Masuk sini, keluar sana. See? Without the image of the hand, it shows like this. Masuk sini, keluar sana. Masuk sini, keluar sana. So what pole will this be? This will be the south pole of a magnet. This will be the north pole of a magnet. Like that. And previously we saw that an electric current exerts a force on a magnet, which is the compass needle. Then by Newton's third law, which is the action and reaction, a magnet also exerts a force on a current carrying wire. When there's action, there will be a reaction. Remember our Newton's third law? I hope you still remember. We have first, second, and third. This is the third law. Whenever there is an action, there will be a reaction. Okay, ada tindak balas balik. So a magnet also exerts a force on a current carrying wire. So experiment indeed confirm this effect, first observed by Ørsted, by the Hans Christian Ørsted. It's like this. Suppose a straight wire is placed in a magnetic field between the poles of a horseshoe magnet. This is a horseshoe magnet. This is the north pole of the horseshoe magnet. This is the south pole. And there is a current carrying wire, okay, in between the north and the south pole of a horseshoe magnet. So when a current flow in the wire, the current flow, where is the direction? Of course, the current, remember the negative terminal of the battery, they are producing the electron, the mobile electron. The mobile electron will move from the negative terminal to the positive terminal. So the current, the electrical current is actually the movement of the positive charges, the holes. So the direction of the electrical current will be from the positive terminal of the battery towards the negative terminal of the battery. And of course, they will follow the routes with the external circuit. So this is direction of electrical current. It is opposing the direction of the movement of the mobile electrons. I hope you still remember this. Now, when a current flows in the wire, experiment shows that a force is exerted on the wire. The force will be exerted on the wire. But which direction? If this is the direction of the magnetic pole and this is the direction of the electric current, which way, which direction, towards which direction will the wire being deflected? But this force is not towards one or the other pole of a magnet, instead directed at right angles to magnetic field. For this case, this wire will be deflected downward. How is it? How do we determine the direction of the force? It's like this. Okay. So now we try to reverse the current. We change the terminal of the battery. Now the electrical current moves at this direction. The horseshoe magnet still at same location. This time, this wire deflected upward. The force this time going upward. Why? This is very strange. By changing the terminal of the battery, the deflection of the wire has been changed. Why is it happening? Actually, we use our second right hand rule. You could use like this, or you could, okay, let me draw one more. There are so many rules in the textbook and all are correct. This is one of the rule. This one also correct. So stick to one rule only. Or you could always use like this. This is your thumb. This is your index finger. Okay, this is your middle finger. And the rest of your finger should be duduk diam-diam dekat sebelah dalam ni. The rest of your finger. Okay, this is your thumb. This is your index finger. This is your middle finger, not ghost finger. This is your ring finger. This is your pinky finger. Pinky. So in the second right hand rule, you only use your thumb, your index finger, and also your middle finger. And your thumb is showing the force, your index is showing the direction of the electrical current, and your middle finger is showing the B, which is the magnetic field. So many books will show you so many way of right hand rule. They are all correct, and this is one of them. So make sure in DUF 1113 you stick to the rule that I have shown to you like this. Okay, use this one. Use your thumb, index, and middle. Your thumb is F, your index is I, your middle finger is B. F-I-B, not FBI or BIF or BFI, F-I-B. Starting from your thumb, followed by your index, and finally your middle finger, F-I-B. Okay, use F-I-B. How to use it? So realign your right hand, follow the direction of I. So I is going over there. Oops. Ni I. B ke mana? B ke from north to south. So if it is the I, this is the B. Where is the F? Align your align your index and middle. Your index finger is showing this direction. Index finger follow this direction. How about middle finger? Middle finger follow this direction, the B direction. So index over there, B over there, and finally you will get your thumb is showing upward direction. This is your thumb. This is the force. So direction of the force determined by the thumb. Realign, practice using your right hand rule. I cannot be beside you to show how to do it correctly, but you should be able to practice on your own using the similar procedure that I have shown to you. Now, again. So on a diagram, when we want to represent an electrical current or a magnetic force or a magnetic field that pointing out of the page towards us or into the page, we use this symbol. Okay, dot or an X. What does it mean by X? X means the direction is into the page. What does it mean by dot? Dot means the direction is pointing out of the page. This is our page. Yeah. Let's say we want to, okay, this is our page. This is our page. This is our page. Let's say we have force going into this page. We use this symbol. It means that, okay, the X, there is a force going into the page. And for example, how are we going to say that the direction of an electrical current is out from the page, electrical current? We use dot. Sini, it means that the direction of the force ke, the electrical current ke, the magnetic field line ke, it's going out from this page. Anything, whether it is FIB, F ke, I ke, B ke, if they are coming out from this page, we use this symbol. If they are, so this is out. If they are coming in from this page, we use this symbol. Now, magnitude. There's a pointer. So experiment found that the magnitude of force is proportional to the current in the wire. The force that we have determined using our thumb in right hand rule is proportional to the current. Bulatkan. Proportional to the current. Okay, the I. And to the length of wire exposed to field. So we have three parameters that is correlated with the force. which the direction has been determined by our thumb. And furthermore, if field B is made stronger, the force is proportionally greater. If B is higher, the force will be higher. So the force also depend on the angle. What else? Angle pun ada main peranan. Angle what? Angle between I. Remember, angle between I and B. Remember we have our thumb like this. We have our index finger, our middle finger like this, and the rest of the finger is like this. So this is F, this is I, this is B. So the magnitude of F is depending on the I, on the B, on the length of wire, the theta. Okay, the theta. So we have 1, 2, 3, and 4 parameters that will determine the strength of the force of deflection of the wire. What is theta? Theta is the angle between I and B. This angle between I and B. This angle. If the theta is 90 degrees, this is the maximum. We will get maximum, the highest force that we could have. But if the theta is lower than 90 degrees, the force is lower. How are we going to calculate that? So we have all the clues. We could formulate them into one formula. Ini je formula dia. We use ILB sin theta. Remember, we have 4 parameters. This is the first one. This is the second one. This is the third one. And this is the fourth one. Congratulations, we have 4 parameters included in the formula. Berasal usul daripada hukum tangan kanan tadi je. Use your right hand rule. And we have F equals to ILB sin theta. And theta, always remember, this is the angle between the I and also B. The angle between I and B. It is not always 90 degrees, but if it is 90 degrees, the force is strongest, as I mentioned over here. Because sine 90 degrees equals to 1. This is the strongest. So if the theta is 90 degrees, the formula we could use like this. F equals to ILB. Because why? Because sine 90 equals to 1. Boleh omitted lah daripada the formula. Now, if I is parallel to the field line B, I is parallel. Your middle finger and your index finger, they are at the same direction. Okay, let's say our thumb is like this, and our index finger is like this. Our middle finger also like this, and the rest of the finger is flipped like this. Okay. If I and B, they are at same direction, which means that theta is 0. Therefore, sine 0 equals to 0. And if sine theta equals to 0, our F will be 0. There is no F. Nampak? Kalau theta kosong, there is no F. Macam tu. Right? Tengok lagi. This is consistent with the definition of the vector cross product. Okay, F equals to ILB sin theta. This is actually F equals to I L cross B. It means that if we saya bukan melukis benda bukan-bukan. Jangan fikir lukisan saya memang teruk, tapi saya tak lukis benda bukan-bukan. This is I, this is B. This is I cross B. I cross B, dia akan berikan jawapan F. So F is the product of I cross B. How do we use the I cross B? I cross B is force. I cross B means that, nampak dia ada cross. Kita akan dapat I, L, B, sin theta. Cross ni kita terjemahkan kepada sin theta. Alright. So the SI unit for magnetic field is B. The SI unit of magnetic field is Tesla, T. B ni simbol untuk magnetic field. So 1 Tesla equals to 1 Newton over ampere meter or 1 Weber per meter square. So we use 1 Tesla. That will be easiest. So we look at example for a while. How many examples do we have? Okay, we have few examples. Let us look at them one by one. A wire carrying a 30 ampere current. Bukan 30 tu kuasa negatif ampere, tak. This is our I. We have the magnitude of I. We have the magnitude of L. Okay, we have the first parameter, second parameter. What else do we have? We have theta, third parameter. Okay. The magnetic field also given. Fourth parameter, complete. What is the magnitude of the force on the wire? Simple. F equals to I, L, B, sin theta. Please, dear students, the formula is given in any examination. Just, if the question is like this, looks like complicated, but actually you just need to plug in all the parameters. I is given, L is given, B is given, theta is given, and the formula also given. You just need to plug in. Masuklah saja formula. It's ILB sin theta. I is given, L is given. Make sure in meter, everything in SI unit. This is ampere. This Tesla also already in SI unit. Sin 60. Straight away using your calculator, please. Just give some little effort. Turn into the final page of the examination question. Find the formula for magnetic field, the force on magnetic field. Plug in all the parameters. You will get the answer. 2.8 Newton. As simple as that. Now, example 2. A straight wire of length 2 meter. Straight wire of length 2 meter. Nampak? L dah bagi. Carries a current of 24 ampere. This is the current. This is I. It is placed on a horizontal magnetic field. Okay. The wire makes an angle of 30 degrees with the magnetic field. The wire carry the current. Magnetic field is B. Yes, this is correct. This is the angle between the I and B. This is the theta. So we have theta over here. If the magnitude of the force on the wire is given, now this time the force is given. What is the magnitude of magnetic field? B. We want to find B. We just need to modify the original equation. Nampak ni? Modify it. Okay, but anyway, before modification, plug in all the parameters. F is given. I is given. L is given. Theta is given. Now we could find B. Rearrange. You just need to rearrange the equation. You find B is 0.02 Tesla. Very simple. Right? This is quite tricky. Okay, now look at this one. A long wire carries a current of 6 ampere in the direction of 30 degrees north of a 0.04 Tesla magnetic field. What are, okay, this is our first clue, Our first clue. No, this is our first clue. We have I. 30 degrees north of a, this is I, this is B. This time it is not 90 degrees between the I and B. It is 30 degrees north. Look at your north, buat lah. Okay, this north. Okay, this east. We have the magnitude of I. We have, okay, 30 degrees north of a 0.04 Tesla magnetic field. We should put like this. Counterclockwise direction, 30 degrees to the north, like this. So this is our B. And our B is 0.04 Tesla. And this is our I. This is 30 degrees to the north from the magnetic field. And our I is 6 ampere. What are the magnitude and direction of the force on each centimeter of wire? Why do we use sine in the formula? We use F equals ILB sine theta. So from the right hand rule, we need to consider the component of F, I, B, which are perpendicular to each other in the equation. Macam mana kita nak guna FIB ni? Macam kita nak guna FIB, sedangkan semua ni sepatutnya 90 darjah antara satu sama lain tak? F ke sana, I ke sana, B ke sana. F dengan I 90 darjah. I dengan B pun 90 darjah. Tapi dalam ni 30 darjah. Macam mana kita nak tentukan? Pak, ni 30 darjah. Nak guna tangan, dia semua 90 darjah. How are we going to do that? Now, we need to resolve. Resolve what? Resolve the I like this. Pak, I draw these imaginary lines. Resolve I into X and Y component. So we have IY and we have IX. Pak, we resolve them. We have learned this in our third chapter or even second chapter. It's a vector resolution. Okay. Now, IY we could always reposition like this. This is how I reposition IY. Pak. So we will have this imaginary triangle. We have IY over here, Pak. IX over here, I over here, and 30 degrees over here. Can we determine IY and IX? Yes, we could find the IY and IX. Okay. And we can always save our energy by considering only the component which is perpendicular to the B. Why perpendicular? Why we must consider the perpendicular only? Because we want to use our right hand rule. We want to find the component of I which is perpendicular to the B. Kita nak pilih yang 90 degrees je. Tapi kalau kamu banyak sangat tenaga, tak ada masalah. You always could calculate the IX as well. IX boleh, IY boleh. And later we will find which I will be used in the equation. So for this case, I choose to calculate IY only. Why? Because IY is 90 degrees with the B. Why we consider B only? Because our theta is the angle between I and B only. So we consider I and B. How about F? F, forget about F just for a while. Okay. So now, what else? So IY, the formula is I sine 30. I have teach you how to determine the IY and IX. I hope you still remember. Refer to chapter 2 and chapter 3. So now we have, this is the reason why we use the formula of sine theta. Remember? Now, insert IY into ILB. F equals to ILB. So our I is I sine theta. Our formula has become F equals, it's actually like this, I sine theta equals to F equals pula times times LB. Ini formula sebenarnya. Sin theta ni belongs to I. Which I? IY. I sin theta is our I. Y. Times LB. This is the origin of the sine symbol in our formula of F. Now, so this is the answer. Okay. This bukan IY, this is I sin theta. Ini silap, bukan IY. This is I sin theta times LB. And we always could rearrange formula. ILB sin theta. Senang cerita sebenarnya, masukkan je formula. Okay, masukkan je formula sebenarnya. Tengok soalan balik. I dah diberi. L dah diberi. B dah diberi. Theta dah diberi. Masukkan je formula sebenarnya. Saya terangkan panjang-panjang tu nak tunjuk kamu daripada mana datangnya sin theta ni. Supaya bila ada soalan-soalan kebat, kamu boleh ikut balik formula yang asal ni. Kamu boleh je masukkan terus. Okay, tapi kamu kena tahulah juga daripada mana asal usul sin. Kenapa saya pakai sin? Mungkin satu hari nanti kita terpaksa guna cos. Macam mana nak guna cos? Bila nak guna cos? Tengok balik. Inilah fundamental knowledge yang kamu perlu tahu kalau nak guna cos ataupun sin. Tapi buat masa ni tak perlu fikir dulu. Itu nanti mungkin bahagian degree nanti kamu akan guna. Kena ingat, inilah slide, inilah yang kamu akan gunakan untuk perkara-perkara kebat nanti. Buat masa sekarang ni, masukkan je nilai dahulu. Okay. Pak ni. So, what is the direction? Okay, you have the magnitude. Remember, force is a vector quantity. So, it has magnitude and direction. Use your right hand rule. Okay, this is your right hand rule. Okay, realign your right hand rule. You will find that the direction of the force is towards the paper. Considering that your index finger is showing upward, your index fingers showing to your right. Okay, tunjuk right. Okay, jari hantu tunjuk kanan, jari telunjuk tunjuk atas. Kamu punya ibu jari akan tunjuk menghala ke dalam muka surat ini. Dia akan masuk ke dalam. Okay, masuk ke dalam maksudnya kita kena buat simbol X. Capital punya force akan masuk ke dalam. Alright. Exercise 1 saya dah buat video exercise 1 dan exercise 2, rujuk kepada video-video saya dalam YouTube ya. Itu saja. Kita sambung lagi untuk 7.3 dan 7.4 sekejap lagi.